Okay, in a recent discussion, there was a question as to how do we ring close. I might have said this in the class sometime, that anytime there is a possibility to carry out an intramolecular reaction, the reaction will go through. And so, for instance, in this particular given situation, you were asked to come up with sort of the mechanism. So mechanistically, you have hydronium ion, which has a positive charge. So first step will be the protonation, which will release the water, and that will generate a positive charge at oxygen. Now realize you have two choices. You can either show a bond cleavage of this bond, let's call it A, or you can show bond cleavage of B, one or the other. And since this is in acidic reaction conditions, hopefully you can see and appreciate that a more stable carbocation will be generated. So A is going to be more feasible than B, which is why you're going to show the bond cleavage of bond A, and it's going to generate a double bond like that, positive charge here, and an OH. So now this bond can move in between, and a 6-membered ring will be generated. Realize from chapter 4 in organic 1, anytime there is a possibility of forming a 6-membered ring, that is going to occur. So let's just put it as a dashed line. This is my newly formed bond. Those are my two metals, and the OH positive charge is going to go over here. Next, of course, the ring closure has to occur again because we want to get rid of the positive charge. So this double bond is going to attack. So let's just number that: 1, 2, 3, 4, 5, and 6. So that's going to be my 6-membered ring. That's the second 6-membered ring. And this is 1 connected to 6, so your new bond is right here between 6 and 1. 5, 4, 3, and 2. So 6 had a methyl and 5 had a methyl as well. And we have a positive charge then, since 5 will be the one which ultimately lost the electron. That's what you get. And again, there is a proton which is going to go through elimination, and you will end up with your desired molecule. So 2 rings, OH, double bond, methyl here and a methyl there, with 2 methyl groups right next to the OH. Let's take a look at another mechanism rather. I have been given that I have a ketone which contains a bromine at the far end, and you have a reaction ongoing with magnesium and ether that gives you essentially a 4-membered ring. So notice you have 1, 2, 3, 4, and 5 carbons total. In the product also you have 5 carbons total. Another thing I would like to say here is magnesium and ether. For the Br, hopefully you can see that reaction that is going to simply get inserted. So first you're going to show the formation of the Grignard reagent, that is right. And so Mg and Br, and you know that this is going to be negative and that's going to be positive. And so here there's going to be an intramolecular cyclization. Electrons are going to move, so that gives you four-membered ring, you have a methyl, so that's carbon number 1. You have an O negative, that's carbon number 2. And then 3, 4, 5. You still have, so your newly formed bond is between carbon number 2 and carbon number 5. And of course you have your Mg and Br, which is going to associate with the oxygen, the Mg and the Br. And when we wash it with the hydrolysis, essentially with the hydronium ion, when hydrolysis takes place in presence of the acid, it's going to cleave off the bond, and you're going to end up with the OH, as we have seen in the past. The key thing here to understand was that this intramolecular reaction, where a Grignard reaction is being added to a carbonyl compound, so the electrophile and the nucleophile, both of those exist within the system, is what's most important.